with two pieces of meat in the middle, a intermediate surface K from which there's a reflection following the geometrical factor, another intermediate reflection from that surface L to the final surface of interest, and so on. So here's the form of the third one, and I think now you could all do the fourth one, fifth one, and sixth one, so I won't do any more. But anyway, that's a hypothesis. And as we always do in logic, we want to test the hypothesis, validate, verify. So first, as a reality check though, we note that for a black enclosure with a black gas, if you will, the emissivity, well, in fact, there's no gas in this because it's surfaces, but the emissivity of all the surface elements is 1, and the reflectivity is 0 for all of them. So the 0th order term here is just equal to the geometrical factor, and the other terms, the other orders, are all equal to 0 because they have reflectivities in them, which are all equal to 0. So you end up getting Dij equals Fij, which is of course true. We know that to be true, so we passed one hurdle here in our logic. Now I'm going to do a partial validation. We really should do a lot of different geometries and things, but this is just to see if there's any hope of going further with this idea. So let's consider a long, regular hexagonal duct. Here it's long enough so we don't have to worry about the radiation entering and escaping through the two ends. They're really far away. And here is a cross section of this duct. And I've divided up into 60 strips. So the strips run along the length of the duct here. And there's 60 of these numbered from 1 in order around to 60. And I'm going to consider two cases here, an emissivity of 0.8 and an emissivity of 0.2. Okay, so let's look at some results. In this case, notice the red number 1 in front of all these subscripts. This is from surface element 1, which is down here in this corner. Look, from the symmetry of this problem, it's 6 ways symmetrical. That number 1 could be right here, it could be right here, it could be right here, but I'm going to put it there. And so I'm going to calculate and estimate the distribution factors from that strip number 1 to all the other strips. So here's all the other strips, 0, really there's a 1 through 60. And then here are the values of the distribution factors. And the symbols you see here are for the different orders. So like for the 0th order, you have these diamond shapes here. For the first order, you have squares. For the second order, you have triangles and so forth. And as you go down, the size of these contributions becomes less and less as you go to higher and higher orders. And this is for an emissivity of 0.8. And the red line you see there is the correct answer. That's the Dij you get by tracing 1,000,000 rays from each of the 60 surfaces and then averaging all the results out to take out the variability you get from the statistics. So this is, we can think of it for all practical purposes already as the right answer. Now, whoops, there we go. Thought you pulled the hook on me. So here are the percentage errors in the estimate that you get simply by adding up these first two contributions, D0 and D1. Add those together, subtract them from the right answer, which is this thing up here, and you get an error. And the error is generally limited to the uncertainty in the original Dij calculation obtained using the Monte Carlo ray trace method. So you can actually predict an uncertainty in a Monte Carlo ray trace. And the uncertainty for 60 million rays in this case is plus or minus 1.5%. So our estimate using only 2 of these contributions, these first 2 here, is pretty good. It's within 1.5%. Okay, another result now, I've moved the source from 1 to 5, and 5 is right here, because there is a little bit of difference going from here to here. After you get to here, you start repeating everything, so you only have to do a couple of these. Once again, we have 4 orders of estimate down here, and they get smaller and smaller as the order gets higher and higher. And then we have a blue line, which represents the correct answer from the Monte Carlo ray trace, and you have a red line, which represents the sum of the orders, of the estimate terms. And you can see they're pretty close together. And once again, this is for emissivity of 0.8. If you decrease the emissivity though to 0.1, you would probably anticipate that there's going to be a lot of reflections, and therefore you're going to have to use a lot more terms in your sum. So in this case, I've considered the first 6 orders, and the Dij blue line is the real answer. The red line is the sum of all of these things for each of these surfaces. And you can see there's a noticeable gap there. It's 4 or 5%, something like that. So we might conclude that it's going to take a lot more of these orders, if you will. But the 7th order, I tried to calculate, and after 2 months, my little laptop is still chugging along. So, you know, there's a practical limit to this also. Okay, conclusions. Radiation distribution factors can be expressed in terms of a series expansion of geometrical factors. Accurate results can be obtained using only a modest number of these terms if you have a large emissivity. But if you have a small emissivity, it's going to take a lot more terms because of all the reflections going on. Obviously, further investigation is going to be required to establish any kind of meaningful relationship between emissivity and the number of terms required, and of course, a variety of geometries would be needed also. So.
Thank you very much. Very interesting work. Do you have a question for Professor Mahan?
Yes.
So you talked about those intermediate surfaces, and I'm not super versed in kind of radiation and all of that theory, but are those kind of theoretical surfaces, or are those actual?
No, those are actual surfaces. The ray trace was really done, and then the estimate was just based on, well, it was just based on geometry factors. And the geometry factors are calculable, you know, for all of these.
Sure.
So the point is, if you can calculate the geometrical factors exactly, and then you can combine those in a rational way and get a good estimate of the distribution factor, which otherwise it would take you a week to calculate on a computer, but here it takes a few minutes or even a few seconds. So you save a lot of time by using this method. Yeah.
I saw somebody who said I to J or J to I.
Yeah.
We give the same thing? Or
When you formulate those 2 equations I showed, the system of n equations, when you formulate them, the natural order is J to I, but then you use reciprocity to eliminate, you know, to reverse I and J. And there's an interesting paper coming out about that.
That's what I'm more interested in.
Yes.
Okay, so we have the view factor leading to that radiosity thing where you get simultaneous equations for the radiosity involving the view factors in the property. Could your set of equations be rearranged algebraically to be equivalent to that?
That's a really intriguing question, and I would say probably. For example, you put it on, you know, Mathematica or MATLAB, and they could probably come down to 2 or 3 pages.
I wouldn't want to try the algorithm, but should that be possible?
Well, yeah. Remember, the way I'm doing it is an admitted approximation from the beginning.
Yeah.
And we just tested it to see how good it was. But it certainly isn't an analytical solution of F equals.
It involves the same stuff, you know, it's like. You know,
Yeah, I know. We know that relationship exists, but it may not be findable.
Yeah. Okay. Thanks.
Thank you very much. And we have Assistant Professor Say.
Yes,
Who will be presenting this work. You advance. One more try. Should show up.
Hello everybody. In this presentation, I will talk about my paper, characterization methods for biomass materials and optimizing heat transfer by using genetic algorithms. My name is Hossein Saad. I'm a PhD candidate at Imperial Aeronautical University, Florida. I also am one of the faculty member in Aeronautical Technical University in Iraq. The other team with my work, Dr. Ers Dikci, is my advisor, and the other team, Christopher Garland, and Dr. Anthony Corey, and Dr. Margot Agricultural waste, let's talk about our abstract. Agricultural waste products can be effectively used as naturally sustainable alternative to insulation materials. So we chose two biomass materials like oak leaf and berry seeds. They are collected from nature. We crush it. After that, we did physical properties of these two biomass powders. So one of these physical properties like bulk density, the other one moisture, angle of repose, and static angle of friction. These just for powders. After that, after we got these, we manufactured these two powders in composite materials by different weight ratios. Then we measured the densities and thermal conductivities of these composites materials. After that, we got properties for these composite materials. Then we compared with the other properties for common industrial or common industrial and insulation materials. For example, we found these two materials, the physical properties of these two materials, the same as the properties in backlight, plasterboard, anthracite coal, flow elastomer, neoprene rubber, and diatomaceous earth. The other part of our work is optimizing heat transfer. A numerical optimization framework based on genetic algorithms is discussed to systematically alter geometric parameter for insulation design. I will talk about that later. Everyone wondering about one question: what are the natural fibers or biomass fibers? Biomass fibers or natural fibers are considered as one of the most important components in different manufacturing applications like textile, paper, packaging, and building materials. Also, natural fibers are a good insulation materials. The natural fibers are eco-friendly. That's the big important for us because we are dealing with sustainable thing for why we are using these biomass materials, because they are sustainable. Also, they could decrease cost, density, and mass. A lot of industrial applications, industrial factories, I mean in the aircraft and automotive applications, they use these because they are decreased in weight. Our experimental methods. For example, we have two biomass materials. This image for berry seeds and this is for all three. For example, we took this berry seeds and we crush it in the grain grinder, mechanical grain grinder. Then we sieve it in sand shaker. Then we got, this is to prevent courses, particle courses. Then after that we got two powders. This is berry seeds powder, and this is oak leaf powders. We did some physical properties for that. For example, we used the AM scope B100 device microscope to examine both these materials. And also we used manual relative humidity. This is manual humidity meter to get the exact moisture percent. Then we use this, the other physical property is bulk density of these two powders. For example, we used picnometer. This is our density cup, 50 mil picnometer. We put this powder, for example, this is oak leaf powder. We put it and we tap it 5 times to make sure there's no cavities. After that, also we have to reach to enclosed system. Then we apply it here in the turbo device to measure the exact mass for this powder, for each powder I mean. After that, we apply this equation normal equation, mass divided by volume, to get bulk density. We run this 5 times per each powders to make sure about the average of that order. Another physical properties we use, this is flowability measurement. Actually, we installed this device by using a funnel with the volume 0.21 liter, and the distance between the end of this funnel and the test surface was 75 millimeter. Actually, we poured the powder in the upper stage of the funnel, and after that smoothly and continuously distributed to get a heap of conical shape of this powder. Then we could measure the height and radius of this heap. After that, we could apply this alpha equals tan inverse h divided by r to get angle of repose for each one. Also, we run it, this is 5 times for each powder. The other one, the other physical properties, static coefficient of friction measurement. We use actually 4 different surfaces, like this one, aluminium, and plywood, paper, and rubber. Actually, we put this heap. After that, we have 2 ends. This is a free end, and this is a fixed end. Slightly and continuously raise it little by little, and gradually enter the whole heap, the whole powder is pulled down in the fixed point. Then we have stand to fix the inclination angle. After that, we could use this protractor to measure the angle of static coefficient of friction. Then we applied mu equal tan alpha. Actually, for the flowability, and this is for static coefficient of friction, we used the same amount, 25 gram per pound. After doing this, we have to manufacture these powders in a composite materials. Actually, the hexanapon epoxy resin was used for making these composite powders. Then even epoxy is mixed with epoxy with parts per 100 resin or rubber of 33. So the biomass fibers, we added 10%, 20% by weight for oak leaf reinforced composite. And we also added 10, 20, 30% by weight for berry seeds reinforced composite. Why we didn't put more than this percentage? Because it will be more viscous. That's why we didn't add more than these 2 percentages. Density of sample. Actually, we measured bulk density for the powders. Right now, here for the composite materials, how could we do that? Actually, we don't have a uniform or homogeneous volume for these composites. So we did, for example, this is a piece of composite materials. This is density, turbo density analyzer kit. This is an accurate device. We could measure the weight, dry weight in air and dry weight here in the water based on buoyancy, and also based on Archimedes principle. We will get a pure density, salt density for that. And this device could give us the salt density and liquid density. Just we are dealing with the salt density. Another thing, the thermal conductivity of sample. We use this device, TPS, this TPS thermal constant analyzer to measure thermal conductivity via composite materials. Another section of our research, optimizing heat transfer by using genetic algorithms. For example, we have this design, and we use genetic algorithms. Let's talk about genetic algorithms. Genetic algorithms are techniques, report techniques, search report techniques that mimic the idea of Darwinian evolution by using rules of natural selection to investigate highly complex multidimensional problems. For example, though there are 3 operators for this genetic algorithm: selection, crossover, and mutation. For example, we have one parent here and one parent here, and they are mating together. This is, it's called selection by, how could we get this by using roulette wheel to pick one parent and pick the other parent. They are mating together to produce a new offspring. This new offspring is called crossover. Then we generate, after generation, we will get many generations for these. What the connection between our work and this work? Actually, we could solve this design direct, I mean analytically, direct analytical solution. But we have to improve this for the next stage of our study. So this is biological study. We convert it to numerical or mathematical way. How could we do that? Actually, we have to set or to alter 5 parameters design. For example, we have K for insulation materials, here insulation materials. We have H insulation, height for insulation, W for insulation, W for steel. This is a steel here, steel bars. And we have thermal conductivity of steel. And the temperature difference is here, 22 degrees centigrade. So, the idea of this work to minimize objective function. This is objective function. This is for your equation, Q equal delta T divided by R total. How can we minimize that? By maximizing R total thermal resistances. How could we use this? How could we get this? By using genetic algorithms, by maximizing the best fitness. Maximizing the best fitness, actually the best fitness maximize our total. So if we got our total here, we will get the minimum optimization for our problem. Our results, this is for biomass materials. These two for powders. This is a scale size of each one, sorry. And for the density and moisture results, we have, for example, here, barley seeds and oak leaves for 5 times we run it, and we have standard deviation for that. After that, we could see from that barley seeds powder are finer in size than oak leaf, and we have 7.7% moisture, and we have 10.5 moisture for the oak leaf. And we have flowability. We could see from this oak leaf is better than excellent flowability than barley seeds due to angle of lower angle of repose. And we have here the highest static coefficient of friction was in plywood surface, and the lowest static coefficient of friction was in aluminum and paper surfaces. And this is, for example, further examination could give idea on how biomass powders stick. We will use the other biomass materials like jute and straw in the next step. Also, we have, for example, here this is for composite materials. We have, this is density. This is neat, pure. There is no. We added 10%, 20%, and we compared this neat with the lowest amount of oak leaf, and we compared this with our amount of barley seed, and we got, for example, here density was found to be reduced with the biomass powders added to the neat epoxy, and the same with the thermal conductivity. This is neat with the 10% and with the 20% of barley seeds. And we have, this is genetic algorithms right now, the other part of ours. As you see here, we have limitation from 1 to 4 centimeter. This is based on the probabilities of genetic algorithms. And when we got the minimum one, WS 1.23 centimeter, and so on for the other thing. And K in insulation materials was 0.007 watt, and this is, it could be matched with our search, or I searched about this number, and we got for this amount is Kingspan optimum as optimum R as an insulation materials. We could pull it into this sandwich for this design. Then we got from genetic algorithms 2.67 degree centigrade per watt. This is for what? For our total, and we applied that third equation, objective function. We got 8.2 watt for the heat transfer. And we applied 100 generations, and we could apply more than 100 generations, but it's the same because this is not, there is no changing in that curve. And for this design, we did this for one objective, single thermal objective optimization, and we will do that for multi-objective optimization by using quantifying this sustainable by maximizing sustainability of this design and minimizing carbon footprint for this design in the future, in the next future. And we will use the same genetic algorithms. We did this, we built this code in C++ to verify this problem to the next step. And we will do the way for this optimization, the way Pareto front to get the best point of compromising between these multi-objective functions. Conclusion, characterization method technique of two types, materials like oak leaf and berry seeds are discussed, and we did physical properties of these two powders, and we measured the thermal conductivities and the densities of these composites. And the oak leaf and the berry seeds, reinforced composites, are shown to be good potential insulation materials, and a numerical technique by genetic algorithms to full insulation materials based on our design. This is my references, and thank you for your attention. And
Thank you, very interesting work. Do we have any questions from the audience? Yes.
So, when we are talking about the insulation properties of these materials, how are the insulation properties related to the flowability and the coefficient of friction that you measured?
yeah, this is, for example, actually, in the beginning, we have powder. We are not dealing with the mechanical properties. This is not chemical properties, just physical properties. One of the physical properties, wall density, flowability, static coefficient of friction, moisture, and the others, for example, melting point, if you want to measure, or etc. That's why I did. For example, also for pharmaceutical industries, they want to know the exact flowability, because if we don't know the flowability by using this powder, we cannot do the next step of composite materials.
From the manufacturing point.
That's why. Any questions?
Wonderful. Do we have any further questions for the next presentation?
Yes.
I saw the one label is at 10%, 20%.
Okay.
One is 10, 20, and 30. What is the reason you missed the 30% one?
Just one second. I have two. For density or thermal conductivity, you are mentioning.
Hey, you have two different kind of parameters, like 10%, 20%, 30%, right?
Okay.
One of them you're showing 3 of them, one I'm showing 2 of them.
Okay. Why? Because if I do, for example, for oak leaf, 30%, the same as berry seeds, it will be more moist, more viscous. That's why I have limitation for that. I did berry seeds 10, 20, 30%. On the other hand, I did, for example, 10, 20, that's it. If I do 30, it will be more viscous. That's why I cannot do it. Thank you.
Once again, thank you very much. Apologize for going slower, but we're in the last session of the day, so let's give everyone a chance to present their work. You all traveled a great distance to come here, so.
What else did you do this evening?
Casinos.
That's true.
All right, our next presentation is by Ms. Wismer on integration of computational fluid dynamics into an introductory fluid mechanics course. We'll round out our last two talks in the realm of engineering education.